Got it. All right, I'll begin with a word of prayer. Heavenly Father, we thank you for this opportunity we have just to meet together and study your creation. We thank you for lead groups, because they're awesome. And help us to enjoy this math. Lord, in your name I pray. Amen. This will greatly annoy some people watching this video. Sorry about that. But you really can skip over the prayers if they are offensive to you for some reason. Yeah, I know, right? So we're going to let John Stillwell be our guide. Naive lie theory. No, I'm sorry. This book is full of naive lies. I was just looking at this title, like thinking about how the general public would like understand it. No.
How long have you been preparing that joke?
I've been preparing that joke for about 2 hours. It occurred to me. I went home for lunch and I was just talking to Jenny about my day, and it occurred to me, oh, that's how other people would look at this book. But no, of course it's Lee theory. What's his name? Sophius Lee.
Why is it
Sophus.
naive?
Oh, okay. Naive is a homage to that book, Naive Set Theory by Halmos. So it's kind of a pun. But anyway, so we're going to look at chapter 1. So basically this course is on matrix Lie groups, right? And so what is a matrix Lie group? It's a group in the sense of abstract algebra of matrices, right? So the group multiplication is that of matrix multiplication. So the identity element of the group is just the identity matrix. The inverse is just the ordinary inverse of matrices. And of course matrix multiplication is associative, so there you go, it's a group operation. And then, as he explains in here, these matrix Lie groups, well, the Lie has to do with being not just a group, but a continuous group. I mean, for example, you could take a finite group of matrices that form some kind of group. They wouldn't necessarily be continuous. They could be like a discrete group, something like, say, rotations by 60 degrees about some axis or something. Or just in the plane, let's say rotations about 60 degrees, right? You have 60, 120, 180.
Or just like I and negative I.
Or I and negative I. Something with a finite number of elements, and it's all closed under multiplication and inversion. So those would not be Lie groups. Those would be maybe a finite group, right? A Lie group is an infinite group. It has some notion of continuity, and you can not just do group operations. You can also do calculus in the group. You can define Lie groups more abstractly to be a manifold with group structure. And then to talk about what a manifold is properly, you need to talk about atlas and some topological notions, and there's more to it, right? We don't want to have all that baggage in here. So I've chose Stillwell's text because he allows us to just look at honest to goodness matrices, and so that notion of smoothness is the technical thing for manifold theory. That's replaced in here, as he mentions over here on page 4. He says a matrix Lie group is a set of n by n matrices for some fixed n that's closed under products, inverses. Now there's no surprises there, that's just ordinary group theory. And non-singular limits. I'm not quite sure what that means. He describes it a little bit more technically here. He says the closure condition means that if A1, A2, A3, A3 is a convergent sequence of matrices in G, and if the limit as k goes to infinity of a sub k is a, then that has an inverse, then a, which has an inverse, then a is in G. So in other words, you have a convergent sequence of matrices converging to something that's got an inverse. So I suppose you'd like for it to be in the group. Well, then it is. Somehow that technical condition on non-singular limits encodes the smoothness. I'm not quite sure how that all plays out, but we'll find out. All right. Any questions so far?
Sounds like when you call the real numbers complete, about like how the limit of the sequence is. I don't know.
Kind of like completeness for a real number.
Yeah.
The Cauchy sequence is converging. Yeah.
That's what it reminds me of.
It is reminiscent of that. I will agree. So chapter 1, he mostly is looking at rotations. either in the plane or R3, and he introduces complex numbers and then quaternions. So where should we start? Do you guys have any questions about? I guess you haven't had a chance to read it yet, unfortunately. But
Hope that I get it before next class.
yours is in the
It's in the mail.
in the mail.
Yeah. Well, I hope it's in the mail. They might just be lying to me.
I see.
I've heard of that before.
Oh, yeah. I hope that's not the case. I mean,
They say it shipped and it actually hasn't shipped.
Ah, yes. Let's see here. So let's look at a rotation in plane. That's a pretty good place to start. Let's see here. I'll try to draw this picture. So, well, I mean, he looks at this specific point, which is kind of helpful. And then he looks at rotating it by theta. Of course, you know, the coordinates up here are what? They're
Cosine theta.
cosine theta, sine theta, yeah. And let's see here. Oh, you know what he's doing? He's like, why is he looking at this? And I know what he's doing. And this kind of sneaky. Why look at those two? So if that's,
Preserves and angles.
yeah, let's see. So same theta. What would this thing be then?
Negative cosine theta, sine theta.
Or negative sine, negative sine theta.
Yeah, notice the theta's on.
Oh, yeah.
It's
So negative sine theta.
yeah. It's kind of. See, I always get the physics. I always get physics with this stupid thing. Like this is a source of perennial confusion.
I just tilt my head.
Just tilt your head. Yeah. So minus sine theta, cosine theta, right?
Yeah.
Now the other thing. So now if you also agree with me that rotations are a linear transformation, then you understand why we're done, because he's just showed us what. He showed us how the this is E1, right? And this is E2. These are the standard basis vectors, right? So we've got like T of E1 is cosine theta, sine theta. And we've got T of E2.
Right, so then you have the columns of the.
Yeah. So if I was to write these more civilly, I mean, without using my silly change a column vector into a row vector shorthand, So there's what they really are in terms of the matrix structure. And of course we know that T of E1, that's the first column in the standard matrix, that's the second column in the standard matrix, right? So if R is the rotation from R2 to R2, it's a linear transformation, the matrix of R, which we'll just call R because we're lazy, is cosine theta minus, cosine theta sine theta minus sine theta cosine theta, right? So it's kind of neat. Anyway, so that's a rotation. Now, what makes rotations interesting, of course, is that, what makes a rotation a rotation? I guess we sort of have some kind of geometric idea about it, right? What happens if you say this is a rotation by theta, right? What happens if we do a rotation by theta? Come on. A rotation by theta, then a rotation by beta. Okay.
In the same plane.
Right, and just we're talking about 2 dimensions at the moment.
That
Yeah.
would be a rotation of theta plus beta.
Do you agree, Bradley?
Mm-hmm.
Yeah. Now geometrically that's obvious, right? If you rotate by theta and then another by beta, then it's the same as just theta plus beta, right? But to check this identity,
Do matrix multiplication.
just multiply by matrices and use the adding angles formulas, and out it pops. Okay, so rotations in the plane, of course, are interesting, but another way we can look at this is in terms of complex numbers, right? Take a complex view. We have z equals to x plus iy, right? Which we could write as x comma y if we make the usual identification of I with the vertical axis and the horizontal axis being the real axis. And Stillwell points out on page 3 that each rotation of R2 can be represented by a complex number of the form cosine theta plus I sine theta, right? Let me just, so he says if we look at like z times cosine theta plus I sine theta, we get what? X plus IY times cosine theta plus I sine theta, which is what? X cosine theta minus Y sine theta plus I times
X sine theta plus y cosine.
right? And so then you can, well, I mean, let me just rewrite this. Of course, this is, if we look at this in terms of a matrix multiplication, this is really cosine theta. So I'm kind of flipping and flopping back and forth between the world of two vectors and complex numbers, right? Which of course is the rotation by theta matrix, right? So multiplication by that kind of complex number corresponds to a rotation by theta. Of course, if we've had complex analysis, we're well aware of this, we remember this. This is of course the polar form of a complex number, which basically shows you that, you know, rotations are naturally kind of built into the imaginary exponential, right? I mean, that's one way you might discover this, e to the I theta, right? All right. Now, if you look at these form a group, right? So the set of all rotations in the plane is denoted SO2. All right. Special orthogonal group of order 2. You can. I imagine he gets into this more in later chapters, but I'll just mention it here since we're at it. If R is an element of SO2, what that means, from just a purely defining SO2 perspective in terms of matrix stuff, that means that what R transpose R is equal to I, and the determinant of R is 1. Of course, the condition R transpose R equal to I is the condition that R is an O2. And then the second one is it makes it special. The determinant R equal to 1 condition basically forces the rotations. Well,
Have any reflection?
yeah, there's no exactly no reflections. All right. Okay. So. At this point, he transitions to talking about how to represent matrices, how to represent complex numbers themselves by matrices, which is a topic near and dear to my heart. And by the way, one of the things I would say as I'm reading chapter 1 in Stillwell's, he uses the term number. Let's say something is a number, something's not a number, and I could have missed it. I'm not sure he ever defined what a number was. I gather that he insists numbers have the set. If something's a set of numbers, there's like a multiplicative inverse, and it's commutative. Because he says in one place he says that the Quaternions are almost numbers, but not quite. So he must think that it's not enough to have multiplicative inverses. must also need to be commutative.
Complex numbers and numbers.
Complex numbers are numbers. Real numbers,
Anything with numbers in this thing.
Integers are not numbers.
integers are not numbers. Yeah, very, very good. Integers are not numbers.
0 is an integer.
Well,
Well, I guess it.
2 has no multiplicative inverse in the integers, right? So
Right.
that must mean that integers are not numbers. No, I'm not trying to. I'm not trying to criticize his book. I'm not sure. I'm always interested to know what people mean when they say something is a number or is not a number, because the term number is a little bit abstract.
Like for him, matrices are numbers. In this case.
For me, pretty much anything is a number. So it's not a very. If I tell you something's a number, not a number, I'm just never going to tell you it's not a number. Pretty much is my kind of default. Oh, okay. So let's see here. The other thing that's really interesting, I think, about matrices is that you can model just about anything with, well, so basically the deal is this. If I look at the matrix A, B minus B, A, right? And I look at the matrix C minus D, D, C, and I multiply these, right? What do I get? Oh, I think I did. Is that right? A, D minus B, C. Oh, B, B. Yeah, minus B. I can't multiply.
AC minus B. Or,
Oh, it's A.
it's AC.
I knew something's wrong here. I just
AC.
couldn't. AC, yeah. Sorry. The more paperwork I try to do in a day, the stupider I get. Let's see here. AD minus AD minus BC, right? Now you can compare that with this formal operation, this so-called AB star, right? So if I define this operation AB star CD, if I say that that's equal to AC minus BD, comma, AD plus BC, right? I could do that. So here's something in 2x2 matrices. Here's something about the plane. And I could just think about the formal viewpoint. Formal meaning A plus IB times C plus ID equals to what? Well, AC minus BD plus I times AD plus BC, right? I say formal because I'm just using I as if it's a symbol, and in the formal thing, what I can tell you is that there's something called I, right? And what do we know about it? I squared is equal to minus 1, right? So like, there's this imaginary unit, right? You can imagine something like this. But then the question comes, well, you just made up this thing. How do you know such an object exists? Like, I can think of lots of numbers, none of them square to minus 1. Like 3 squared is 9, square root of 3, 3, let's see here, square root of 2 squared, 2, 1/3 squared is 1/9, minus 1/3 squared, 1/9. I mean, you go on down the list. If you only think about real numbers, the square is always non-negative, right? So people doubted the existence of this for a while. Of course, people doubted the existence of other things like natural numbers, and, well, maybe not natural numbers, but integers. Certainly, negative integers had their trouble back in the day.
0.
0, yeah. Yeah, 0. So I guess the interesting thing here, this 2x2 representation of complex numbers by real matrices actually goes back to Cayley, maybe 1858, something like that. He wrote this down. This I sometimes see attributed to Gauss. Hamilton apparently was definitely doing this. right? Looking at complex number as a pair of real numbers with this funny multiplication, right? So that's kind of interesting. Like Hamilton was looking, he's like, okay, so this is complex number multiplication, right? So like, what if you did a triple? What if you tried to define a multiplication on a triple? How would that work? And he spent like 13 years trying to do that, and he couldn't figure it out, right? Turns out that there is something with a four-tuple that's kind of analogous to this that corresponds to the Quaternion multiplication.
But there's no triple.
There is, though, but not that satisfies other things. The other thing is we want this notion of length, this absolute value. So there's like a quote-unquote absolute value. I would call it a multiplicative norm. There's a multiplicative norm for complex numbers and for the Quaternions, but that's it. You can't build a product on R3 which also has a multiplicative norm. Anyway, so here, there's something specific that's I. I is modeled by just this, right? I mean, that was just in the picture we were thinking about. This times that is, 1 is 1, 0, right? So if you do 0, 1 times 0, 1, you get back to minus 1, 0. So I, quote unquote, is this pair 0, 1 in this model, right? In the matrix model, the imaginary number I is what? Well, I is equal to 0 minus 1, 1, 0. And you can easily see under matrix multiplication that squares to minus the identity matrix, right? The 1 here, there can be only 1. Now apparently there can be lots of 1s. Let's see here. Sorry, Neo. But surely Neo would like the top one. Yes.
He wants to destroy it.
Does he want to destroy it, or does he want to control it?
I only saw the first one.
Oh, okay. I only saw the first one. It's excellent.
He wants to let it kill him.
It's an excellent answer. I was really hoping that, like, I was so disappointed when there wasn't, like, another level of reality. Oh, you haven't seen the... I don't know what happens in those later movies. I can't really say. Spoiler alert, so...
I don't have any intention to watch them.
Oh, okay. Yeah. Anyway, so, which is the complex numbers? This is a philosophical question we can ask. Is the complex number this? Is the complex number this? Is the complex number that? It's all of them, I would say. I would say, well, yeah, these are isomorphic copies of the same structure. I mean, this is begging the question, what is it even? But, as you read undergraduate textbooks, a lot of times they'll pick a specific model and then say that's the thing. And that's important for the sake of not driving students not to actually have a concrete definition of things. Like one of my fundamental frustrations in doing physics homework as an undergraduate, I'd be asked to prove something about a circle. And then it would leave me the question, what is a circle to this book or to this instructor? What am I allowed to say a circle is? Because if I say it's what I'd like to say it is, this is immediately true, so why am I even asked the question? One of the fundamental frustrations of the undergraduate, right? But anyway, these are just some ways of... So the point of this, though, is really we can trade a complex number for a 2x2 real matrix, right? I think that's interesting. All right. And there's other things here. There's goodies to look at. What's the determinant of this matrix? It's a squared plus b squared, right? And you know that the determinant of m times n is the determinant of m times the determinant of n. You should have respect for this identity. This is not a trivial identity. This identity comes at a cost. But hey, it's there. And so what this says, right? This is actually what this is the length of a plus ib. If you allow me to flip back to the other notation squared, right? It's the absolute value squared. So what this then says is that the absolute value of two complex numbers squared is equal to the absolute value of the one complex number squared times the absolute value of the other complex number squared. And so there you go. You have the multiplicativity of the well, I usually call it the modulus, he calls it the absolute value, multiplicativity of the absolute value arising from the multiplicativity of the determinant, which is pretty awesome. Any questions, you guys? You can always interrupt me, ask questions and stuff. It's cool. Oh, the other neat thing, of course, is conjugation, right? Because if we have 1 over, and why does that have anything to do with, I'm not sure that has anything to do with, what does it have to do with matrices? Maybe it's just, oh, right. Something Daniel and I at various, or I think it was, I think I appreciate this Bailey too. All of a sudden it hit me, if I'm working with a set of, so for us, when we think about numbers in the research, like numbers are just some algebra of matrices. What that means is there's some subset of the set of whatever size matrices we're working with, usually real matrices, and they're closed under matrix multiplication. That's pretty much it. And then there's, well, that encodes some kind of multiplication on our end. But the multiplication doesn't have to be nice. We insist it's associative, but it doesn't have to be commutative. It can have 0 divisors. That means that the inverse of certain numbers might not be defined. Kind of like Z6, for example. You can find an inverse of, let's see, in Z6 you can find a multiplicative inverse of 5. Because 5 times 5 mod 6 is 25. 25 mod 6 is 1. So you see 1 over 5 is equal to 5 mod 6. But if you try to find an inverse for like 2 mod 6, 2 times 3 is 0, which means 2 and 3 are 0 divisors. There is no multiplicative inverse for those. So there's that same kind of dichotomy in the abstract number systems we study. Some numbers have inverses, multiplicative inverses, others don't. The ones that don't tend to be 0 divisors. I'm not sure if there's a trichotomy. Perhaps there's 0, there's units, there's 0 divisors. I kind of think there is that trichotomy. And the determinant tells you what's what. Right. The ones that have determinant 0, those are the bad ones. Those are the 0 divisors. And the ones that have non-zero determinant, those are the good numbers. Those are the ones that behave. They have multiplicative inverses. That's true here. The 2 by 2 inverse, right, reproduces the classical formula for an inverse of a complex number as well. Like, what's the 2 by 2 inverse formula? It's 1 over a squared plus b squared here, because that's the determinant. And then you do what? You flip the diagonal. Well, that's kind of, that's hard to see, but I flip the a's. And then,
Change the signs.
right, so minus b. Right, now if you look at that, what that is that's a minus bi over a squared plus b squared in the other notation. Okay. So you can recognize that as being the usual term. In terms of conjugation, we usually say like 1 over z is what? It's z bar over zz bar. That's how you flip, conjugate a complex number to put it back in Cartesian form. So that
is that almost like the like taking the norm and making it 1 in complex? Well, if you're dividing by a squared plus b squared.
Well, yeah. If we knew that z was something, if z was something like e to the I theta, then that would be 1. But in general, it doesn't have to be. I mean, it's the length squared of the complex number. We're thinking about the length, the distance from the origin out to the point. So that's the length. All right. So now there's all kinds of really interesting number theory hidden in this simple construction, because if you look at this and if you look at that, z times w be something like this, right? So let's see here. Let's think about this identity for this calculation up here for a second. What would it say? I need to erase. Oh, I guess I can leave this one. I need some space here. Need some board cleaners. What I need. All right. So the length squared of this is a squared plus b squared, right? Length squared of this is c squared plus d squared, right? The length squared of that that's not altogether an obvious identity, right?
No.
Yeah, that is what's known as the two-square identity, right? Let's see, how do we use that in number theory? I'm trying to remember various things.
We're looking at the numbers, they can be split into sum of two squares, and then showing that if you multiply two of them together, you get another one, it's the sum of two squares.
Ah, so if I have two numbers that are sum of two squares, and if I multiply them, I get another number that's the sum of two squares. Yeah. And then I think you can also look at this in terms of kind of like multiplying triangles. He has a picture. When you guys get the book, or have a chance to read the book, you'll see he's got this wonderful picture of the, was it the Diophantus, or, I don't know, it's old. It's old. Very old. It's fun to look at specific numbers. So, you know, the one way to look at this problem is, okay, so this is, once you have this multiplicative norm, right? You have this absolute value that satisfies this multiplicative property, let's say. You have that, and you've got some product, right? I mean, if I'm talking about multiplicative, I'm already thinking there's a product on the space, right? Then tied with that is some kind of, in this case, two-square identity, right? So by the same token, you could say, is there a three-square identity? Is there a way to write, say, if you have something like a squared plus b squared plus c squared times x squared plus y squared plus z squared, right? Is that equal to something like alpha squared plus beta squared plus gamma squared? Is there a three-square identity? This in turn would be tied to the existence of a multiplicative product on R3, which had an absolute value which is multiplicative. That's the thing that, I mean, so implicitly this is what Hamilton was trying to do. I think what he actually did, if I understand the history as explained in Stillwell, right, he was trying to find the product, but at the same token he's trying to, if he could have, it would have done this. Now it turns out that no such identity exists until we get
To 4.
to 4, and then it's
And 8 too, or not?
yeah, is there an 8-square identity? I think, I don't remember that actually right off the top of my head.
I've heard some things about like the Quaternions, where they're not commutative, but they do have some special things.
Right, there is, the Quaternions are not associative, but they do have special properties, that's true. I mean, so there's a formal process you can get from the reals to the complexes by something called it's called, what is it? Oh man, I can't remember. Something doubling. I forget the proper name to credit this to. And then if you do the doubling process again, you get the Quaternions. If you do the doubling process again, you get the Octonians. If you do the doubling process again, you get the Sidonians. If you do the doubling process again, you get things I don't know the name of, but they're generally called Cayley numbers. They're nasty, they're non-associative, but they are what's called power associative. And there's some guy out there who has spent the better part of his career studying the calculus of these things.
Of like the higher like Sidonians and
Past Sidonians,
Past.
yeah, like the Cayley numbers, the power associative analogs of these.
Hmm.
Yeah, there's a wealth of knowledge out there.
If you go far enough, you go where people haven't gone before.
Yeah, I am content to look at I'm content to look at my quote unquote version of a number, which is for the most part I'm interested in associative algebras over the reals. Yeah, they got some zero divisors, but we've figured out we can do calculus on there pretty well most days. We have a harder time is writing up things about them. I blame Disney World though. It's a good. I have Matrices. We have work to do. So that brings us to Quaternions. All right. Is it okay with you guys if I go a little bit over today since we started stupidly late?
Yeah.
Yeah, I think so.
Okay. So, Quaternions. So you saw some of this last time. Well, not last time, but you saw this last semester in the thing you looked at.
Mm-hmm. Yeah.
He's building complex numbers and Quaternions from real matrices, right?
Right.
So this has some of that same stuff. Like right now, we're talking about how the Quaternions can be modeled by 2 by 2 complex numbers. So, like formally, I would say a Quaternion is something like this. It's t plus xi plus yj plus zk. So I would say that's an element of R, direct sum IR, direct sum JR, direct sum KR. These versors, the quaternionic units, ij is equal to k, jk is equal to I, ki is equal to j, I squared is equal to j squared is equal to k squared is equal to -1. I think if you just write that one identity, what is it? There's a slick way of doing this in terms of one relation.
And then if you flip the orders, they make negatives, like ji is equal to negative k.
Right. It's just like cross product, basically.
Yeah.
So what I'm telling you right now, I would say that's the formal, right? That's like the formal. I've got to find a better way to work with this book. And I like this book, so I don't want to just rip it apart. This is formal. I haven't told you what IJK are. I'm just telling you that there exist these things. They satisfy these rules, like you were just telling me. JI is equal to -k, etc. Now, I'm not by any means claiming this is a minimalist, nor am I trying to be a minimalist. I'm just trying to impart to you information. I set aside the question of how to minimally present these in terms of a minimal set of logical axioms. That's not really where I'm going today. All right. Now you can view these things though as 2 by 2. There's a 2 by 2 complex matrix, right? That encodes these quaternions. How's that go? So something like, let's see here. So of course, let me just try to stick with Stillwell. I'll say A, B, C, D. And I mean so if we were to look at this in terms of kind of a boring, what's that?
It's just a plus bi and c plus di.
Okay.
Negative c plus di, I think, in the bottom.
So what did you say?
It was a plus bi in the first entry, and then the next one was c plus di in the next, yeah. And then I forget what that the bottom left one was, but the bottom right was again negative a plus bi. I think.
Plus bi?
Yeah, I think so.
Nope.
No?
But don't feel bad. There's like 13 different ways to do this.
Oh, okay.
Yeah, that's the interesting thing is if you look in different books, you'll see different representations.
Oh.
So he's got a different one in here. Then again, some of what Tapp does in his book is based on row multiplications. I don't know if that figures into his particular representation choice. But I will be boring and stick with Stillwell here. There's a harder question. What are all possible representations? Oh, let me not ask that. All right, A plus ID. A minus ID. So you see you're on track there. Minus B minus IC. Excuse me, B minus IC. So he says you can define quaternions to be these kinds of 2 by 2 complex matrices if you want. And so let's see here. Um, there is some way of motivating, I think, these formulas. But I don't remember.
Isn't it just to make the determinant real? Or is that always going to happen?
That's definitely part of it. If I call this thing eta, let's say, the determinant of eta is what? What's this? The product of that and that is what?
A squared plus D squared
Yeah.
Right?
Yeah.
plus B squared plus C squared
Right. And then minus what?
Is it
minus B squared.
B squared plus C squared, right?
Yeah.
Minus C squared.
Plus and minus.
See, because when you multiply these, you get minus b squared, you get minus a minus, which gives me I squared times c, which is minus c squared.
Mm-hmm.
And then I get a plus IBC and a minus IBC, so the imaginary terms cancel. And we're left with the 4 square. Yeah. And so then, if I have two quaternions, right, if I have an eta, say eta 1 and eta 2, if I look at the determinant of eta 1 and eta 2, I get the determinant of eta 1 times the determinant of eta 2, and that gives me the 4 square identity. So, I mean, this is what you might call the absolute value of eta squared, right? It's the length of the quaternion from the origin in R4. Euclidean length, sum of the squares. I'm not sure I want to write this out. Let's see here. I guess that's not, well, okay, fine. This is a
I
squared
kind of want to see it.
plus b squared plus c squared plus d squared, all right? Is equal to what? Oh,
No, you need to
No.
it'd be that times something else.
oh, no.
You don't need to do
Plus x squared
Oh.
plus y squared plus
Oh.
c squared plus w squared.
Fine.
that. You can find it in
Is
the
it? It's in the book. Okay, we're good.
It's in the book.
If it's in the book, then you don't have to go through that.
I think you're supposed to show.
Oh, we're supposed to show it. Well, yeah.
Yeah.
Homework.
Homework, kind of.
Huh. Hmm. Alright. Where was I? Well, fine. It is actually important to go through this calculation at least once to appreciate what's going on here. So let me just go ahead and do it. It's, let's say, T1 plus, I need a name, let's say V times T2 plus W. And I'm using vector notation. I mean, V is like, let's say xi plus yj plus zk. Let's say w is equal to ai plus bj plus ck, okay? Calculate this product, take our medicine, see what it is. I mean, it's going to take us a minute or two, but it's worth it. We'll then have that identity and we can understand everything else. Once you understand this product with a decent notation, everything else falls into place. All right. I'm going to collect all the real terms to start with. So T1, T2, minus AX, minus BY, minus CZ. I don't know why I'm writing this ABC first. I did though, so it's done.
Kind of like it that way.
And then, plus I times 1. What are the terms that multiply to I? Yeah, T1, T1A.
Yeah, T1A plus X T2
Mm-hmm.
plus YC minus ZB.
Right? Plus J times what? What are the J terms? Well, the easy part, T1B plus YT2.
Plus ZA
Right?
minus XK.
Oh, not K.
Sorry, C.
X.
C. Yeah.
And then plus K times what? Oh, so T1C plus ZT2 plus XB minus YA, right? So,
I'm just going back and dotting all of them.
so if I was to call this thing, and call this whole quantity, say, alpha. If I was to call this whole quantity beta. If I was to call this whole quantity gamma. If I was to call this whole quantity delta. Right? Then that's what should be here. Not a squared plus b squared plus c squared plus d squared. No. Alpha squared plus beta squared plus gamma squared plus delta squared is equal to the product. So like, this is the eta 1, this is eta 2, right?
Mm-hmm.
So the length of eta 1 is
T1
length,
squared.
yeah, length squared. What's that?
T1 squared plus X squared plus Y squared plus Z squared.
And then T2 squared plus a squared plus b squared plus c squared. And that, where you understand that alpha, beta, gamma, and delta are given as above, not including the versors, just including the real numbers there, that that is the 4-square identity. Which is tied again to the existence of the Quaternions. These Quaternions. Right now, obviously, I mean, there's some things missing from the presentation here, right? Like, I should check that such complex 2x2 matrices, when you multiply two of them, you again get another complex matrix of the same pattern, right? I should check that if you take the inverse of a 2x2 complex matrix like this, it's again a 2x2 complex matrix like that. I should check that the identity fits the bill. A equals to 1, everything else 0. Good, yeah, done. So yeah, they do form a group, multiplicative group under complex 2x2 matrix multiplication, and that, you know, for the non-zero ones at least, they form a group. I mean, 0 is not in the group, but the non-zero ones form a multiplicative group under 2x2 complex multiplication, and that's the group of Quaternion, not a group of non-zero Quaternions. or you could say the group of units in the Quaternions. Any questions? Now, this thing we just worked out, there's a little bit more we can say if we just kind of look at that more carefully. You can see that in fact what this also says is that if you look at V times W, all right, so if you throw away, set T1 and T2 to be 0, right, all of the T1 and T2 terms drop out. And all you're left with is this, minus AX, minus BY, minus CZ. That's exactly the dot product. Right, so that's minus V dot W. I remember calculating this with my brother when we were teenagers in the basement. That was so cool. Plus V cross W. And by the way, these other terms are exactly the cross product. So the quaternionic product of vectors automatically encodes both the dot product and the cross product like this. Yeah, which is cool. Let's see here. I think also of note is the fact that, let's see here, 1 is 1, 0, 0, 1, no surprises there. I is equal to what? J is equal to what? K is equal to what?
It's equal to 0, -1.
Yeah, so basically just put B equal to 1 and the other 0. So what did you say it was?
0, -1.
And then the C's, so it's like 0 minus I, 0. And K was what? DB1.
I. Yeah. -0, 0, -1.
Yeah. That's the particular representation we're using of the group of quaternions into the complex numbers. By the way, representation theory, at least one part of representation theory, involves looking for groups of matrices which are homomorphic to, say, your favorite abstract group. This is a representation of the quaternionic group into 2x2 complex matrices. But the word representation has a lot of meanings, not just that. If you stay in pure math, understanding what this idea of representation theory is, it probably is going to be a big part of your graduate work. Page 8, he has all these fantastic properties of quaternions. They're, the additive structure of the quaternions. It's commutative, it's associative. Got an additive inverse of 0, right? Multiplication's associative, you got inverses. Because it's a 2x2 matrix, so you can write down the inverse. And the inverse, because the inverse is like 1 over the determinant, we already know the determinant is this, right? So if the quaternion's non-zero, this is non-zero. Therefore, the inverse formula makes sense. So every non-zero quaternion has a multiplicative inverse. That's pretty slick. In the algebras we look at, other algebras, things that perhaps Stillwell would not call numbers, this is not a sum of squares. It's something else. So there are numbers which don't have multiplicative inverses. Like one of our favorite examples, it works out to basically, like a three-dimensional example, it works out to a squared plus b squared plus c squared minus 3 times abc. It works out to that, for example. It's fun. There's another three-dimensional example where it would just work out to ABC. Yeah, and of course that's third order, but anyway, that's another story. What's the there's the notion of conjugation here. What's the conjugation of a quaternion? You just put a minus, all right? This is an important point that could get you if you were assuming it, and it wasn't. It's actually not true. The quaternionic conjugate is not the result of taking complex conjugate of each entry of the matrix in Q. In fact, Q bar, the quaternionic conjugate, is the result of taking the complex conjugate of each entry of the transposed matrix. I think you kind of remember some of that, right? I mean, I think...
I'm not sure if I did that.
Yeah. But it may just not have come up in the way you're approaching the material.
Probably.
Yeah. Let's see what Stillwell tells us. He says, the algebra of quaternions was discovered by Hamilton in 1843. That's why we call it H.
Oh.
The matrix representation, though, was discovered by Cayley in 1858, this one. So I think maybe Hamilton just did it formally to start with. Or maybe just with R4, with this, like maybe just R4 and here's the pattern. That's probably what he did, I mean, if I had to guess.
It seems harder.
Yeah. All right. So then he turns his attention to the study of isometries. You know, what's an isometry?
Transformation that preserves distances.
Yes, a transformation which preserves distances would be it. And so we can prove that. Let's see here. I'll try to prove that. I think we're okay to. I'm gonna leave. I might want that, but I'm gonna erase this. Let's check for a second. I'm gonna feel really stupid. Okay, I just feel no, just usual stupidity. Not extra stupidity. Okay. I got new stuff at home, but I just didn't bring it. I even was thinking getting it when I went home today at lunch break, but still no. We worked this out in number theory, you might remember. I think it's worth seeing in 2 courses. All right. So here's a very, very cool calculation. It's like he says, without any computation with cosine and sine, we can see that multiplication of complex numbers identified as R2 by U is a rotation in the plane as follows. Now, what is U? He says, suppose first that U is a complex number of absolute value 1. Okay. All right. So we'll take a point, I guess a pair of points, right? So take any, let U and, he says, let V and W be any 2 complex numbers. So, okay. 2 complex numbers in the plane, right? You guys with me? And so what's the distance between, this distance here would be the absolute value of V minus W. Dr. Schoenborders would be happy. Stillwell also calls it absolute value. I usually call it modulus. I don't know. I tend to insist absolute value is only for real numbers, but yeah, whatever. He's bullied me into the usage. I'm happy. All right, so V minus W is this. That's the distance, right? So what if you look at the distance from UV minus UW? The distance of U times V minus W, right? But the absolute value is multiplicative. And there you go. So therefore, complex numbers, unimodular complex numbers, right? Complex numbers with length 1 are isometries. They preserve the distance between points in the plane under multiplication. He says, moreover, this isometry leaves the origin fixed because U times 0 is 0. But on the other hand, You know, the only point that this multiplication, you know, if you look at the transformation